So for lesson 10.2, we're looking at forms of energy. So just kind of looking at different forms of energy. We're looking at kinetic and potential energy, so hopefully you remember that from physical science and how those are calculated. We're also looking at rotational energy as well, so that will be new for you guys. So the bell ringer we're talking about here. So the difference between kinetic and potential energy. Well, kinetic is energy of motion. And you might not know these off the top of your head, so you might need to look them up. And potential energy is energy of position. Potential energy is also considered stored energy. So there are a couple different things we can look at. So we can look at gravitational potential energy, and we can look at like elastic potential energy. So this could be in like springs or rubber bands or something like that. But kinetic energy is always going to be some kind of movement. Okay, so that's the difference between the two. And can one be transformed into another? Well, think about maybe if you have a rubber band and you're trying to shoot that at somebody, maybe you got your finger up in there, right, and you're trying to blast a rubber band at somebody, so you pull it back, and then so when this is pulled back, stretched all the way like that, that would be elastic potential energy. And then when you let go and you shoot it forward, then that's going to go pretty quick, right? It'll kind of retain its shape, its normal shape, but it's going to be moving forward like that. So it's going to have a lot of kinetic energy after you shoot it forward. I wouldn't say a lot, I suppose. It depends on how massive it is. But yes, you can transform one into another. So you stretch it, that's stored energy, potential energy, and you release it, that turns into kinetic energy. So they do transfer from one to the other, which we'll be talking about in our next lesson in conservation of energy. Okay, so here are a few different types of energy. You might want to read through these and kind of think about. We have translational kinetic energy, we have rotational kinetic energy, we have potential energy. And we've kind of talked about these three already. Rotational, maybe not so much, I just mentioned it. But translational, that is just left and right. So energy moving left and right. Potential energy, we talked about that as stored energy. And gravitational potential energy, I haven't talked about that specifically, but you can kind of put the two together with gravity and potential energy. So how do I get more energy from gravity? That would be the height of an object. And elastic potential energy, talked about that with the rubber band. And thermal energy, I haven't discussed this, but we'll mention it briefly at the end, and how that can be turned into different forms of energy. Okay, so remember in the last lesson we talked about this thing called the work energy theorem. So to remind you of the formula, work equals the change in kinetic energy. So you have a final kinetic energy minus an initial kinetic energy, and you find that change, and that results in the work done in the system, or the work done by whatever object we're looking at. If we're looking at this scenario or this question, how does energy change from one form to another? We kind of already discussed that in the bell ringer question. So that could be the elastic version. It could be stretching something that is rubber or something that is like springy. So you take a spring. So let's say we have a slinky, right? With slinky just kind of sitting there. It's just nothing. It's just sitting there, right? So then we take that slinky and we have one person here and one person here, and they stretch that slinky between the two of them. Okay, when they do that, that is creating elastic potential energy between this distance here. We're stretching it out. And as soon as both of those people let go, then that slinky is going to kind of retract back to its fairly normal shape. So it kind of retract to a smaller shape and then drop down to the ground, and then it would kind of go back to its normal shape. But talking about changing from one form to another, we have the potential energy here when it's stretched out. We have the kinetic energy here when we release it, and then it's back to its normal shape here, okay, at rest. So yes, we can change from one form to another, and this would be an example. The rubber band would be another example of it. And talking about maybe mentioning this early on, gravitational potential energy. Say you are standing on a building and you have a rock or something, I don't know what you want to drop from a building, maybe a penny from the Eiffel Tower, and you want to drop that down. So when you're standing at the top here, depending on how high you are, then that would represent, or that would give you, your gravitational potential energy. All right, so gravity is pulling on this. The further it falls, or the faster it's going to go. All right, so as soon as I let go of that thing, say maybe it's here, then that is going to have a value of kinetic energy because it's moving, right? And it's moving down again. So we talk about reference points, which we'll get to in a minute, but that rock right before it hits the ground is going to have 100% kinetic energy and 0% potential energy because its height is 0. Okay, and we're going to talk about that here in a minute. So I'm kind of jumping ahead. So talking about the difference between translational and rotational kinetic energy. Translational kinetic energy is just our normal kinetic energy equation, which we discussed in the last lesson. This would just be moving left and right, or maybe up and down. Okay, translations can be any one of those 4 directions. We could talk about a movement at an angle or something like that. It's all kinetic energy. Okay, it's just in 2 dimensions here, or it's just left, right, up, down, or at an angle. Okay, kinetic energy can also be in a rotational form. Okay, so that would be called rotational kinetic energy. All right, and that can be calculated using our moment of inertia, so hopefully you didn't forget that. So that is represented by capital I, and its angular velocity, which is the Greek letter omega. Okay, so this is our equation for rotational kinetic energy. And we're going to use that here at the end of the lesson to try a practice problem. So let's look at a scenario that would discuss these. So translational and rotational kinetic energy, we're looking at a diver. Examine the energy of a diver. So right here, diver is not moving, maybe sitting on a board or something like that. So our kinetic energy is 0. And remember, it's joules. And then the diver bounces. So I guess we could say there's some elastic energy going on here, elastic potential energy when the board loads. But we're talking about kinetic energy here. So the diver jumps sideways. Okay, so that would be some kinetic energy going on because we have this mass in movement. Okay, so the mass has some sort of velocity. And then the diver tucks their knees and begins to spin. So when the diver spins, they generate rotational kinetic energy, and wherever our center of mass is, let's say it's right there, the diver is still moving sideways, so there's going to be rotational and translational kinetic energy until the diver begins to fall, and maybe the diver opens up and is going straight down, which results in translational kinetic energy in the end. So at this point in time, with that rotational kinetic energy, we could figure that out with our equation, 1/2 I omega squared, and we'd have to know the rotational inertia of the person here and how fast they're spinning, but that would be given to us, or we could calculate that maybe with a high-speed camera or something like that. So we could calculate that kinetic energy. So a scenario to think about down here, think about a flood control dam. All right, so that would be, maybe if you've never seen one before, they have a certain amount of gates, and there is a river below here, and when it, let's say there's maybe a stream or a lake up above here, so if you know where Gavin's Point Dam is, or maybe Fort Yankton, or Lewis and Clark Reservoir. That might ring a bell. But there are a certain amount of floodgates here, and we're wondering how energy changes in a flood control dam and how it's used in a flood control dam. So we have this mass of water up here, and then we have the river down below here. So when we have this river, or when we have this lake starting to fill up, we might have too much water in there, and then we need to open up these floodgates and let some water out. So this has a potential energy sitting here behind the dam, but then as soon as we open up the floodgates, then the water starts to come out the floodgates, which releases the water and turns into a kinetic energy type of situation. Now there also may be off to the side some sort of generator or building that has a generator in it. Okay, so this would also have water coming through it, which would be released down into the river below, but there would be some kind of a turbine in here that's spun when the water goes through it. Now this is probably going to be going most of the time, but there's still going to be some flood control happening because this might be a substantially large reservoir. Okay, so it's turning potential energy from the water sitting up here to kinetic energy when the water is coming out of the flood control dam. And we take that kinetic energy and we can turn that into electrical energy when we take that through some kind of a turbine. So lots of things going here. It seems really simple. It's like, all right, I'm blocking the water, keeping it from going down, but there's actually, if we think about the physics behind this, there is quite a bit of physics behind a flood control dam. So going more into potential energy, so the main idea, it is energy that's stored, and this could be elastically stored, it could be stored due to height of something, so those are the two main ones. But it's energy that's stored due to interactions between objects in a system. Okay, the stored energy due to gravitational force, that's called gravitational potential energy, and we abbreviate that as GPE, capital G, capital P, capital E. And you've noticed me writing KE and PE for kinetic energy and potential energy, so gravitational potential energy is GPE. So when we talk about gravitational potential energy, we have to discuss some sort of a reference level. So depending on where our reference level is, that's going to change our gravitational potential energy. So you could say, I think we're going to talk about a tennis ball here later on, you could say that the gravitational potential energy, the reference level, could be the ground for GPE, or you could say that the reference level might be the racket for GPE if the person is bouncing the ball on the racket. Okay, so it depends on what we state as the reference level. And here is our equation for gravitational potential energy. So this is the mass of the objects. This is the constant g, which is 9.8 meters per second squared. And this is the height. So talking about reference level, the thing that's going to make the difference is the height. So it depends on what we declare as a reference level. That is what's going to give us our value of height. Okay, so that's very important. So looking at a juggler here, so it was a juggler, not a tennis ball, we need to think about how the reference level affects the values of gravitational potential energy. Am I going to say this is the reference level, so the left hand, or am I going to say this is the reference level, the right hand, or could I say that this is the reference level, the waistline? So we can draw a graph of the different values here. So let's say for this one, this is the reference point of the juggler's hand at the bottom. So we have our ball at the bottom is going to have 0 joules of gravitational potential energy. And then we throw the ball up at the highest point, it's going to have the most gravitational potential energy. Okay? And we can talk about, since we know that kinetic energy and potential energy are somewhat connected, we can talk about the values of kinetic energy with the values of gravitational potential energy. So you're throwing that ball upwards, and we give that ball some kinetic energy in the beginning, right? So then here at the top, since that's the highest point, we know at the highest point of some kind of a projectile motion, okay, we can kind of talk about that here, that the velocity is 0. So our kinetic energy is going to be 0 joules at the highest point, but our gravitational potential energy is going to be the highest value there. All right? So then the ball begins to fall down, and at the bottom, then it's going to have, again, the highest value of kinetic energy and the lowest value of gravitational potential energy, because that's 0 joules. That's back at our reference point of 0. Okay? So just to show you how this makes a difference when we declare our reference levels, let's say our reference level would be the top of the arc, or the highest point of the ball. So here we are below our reference value. So technically our gravitational potential energy is going to be a negative, because if we think about height, say this is 0, then I am at a negative value. Let's say we're at a negative 0.5 meters here. So that's going to make our gravitational potential energy a negative value. But our kinetic energy will still be positive because we are applying some velocity, right? This just is our velocity, and our velocity is upwards. Okay, so at the top here, that's at the top of our reference point, or I suppose that's at our reference point, which is 0. So gravitational potential energy would be 0 because we declared that as our 0. And the velocity is also 0 here, which means kinetic energy is 0. Okay, so you can kind of put these together to show that the reference level is kind of important. And most of the time it's pretty easy to pick out the reference level. It might be the ground or something you're lifting the object from. Okay, so if we talk about maybe theme park physics, this uses a lot of kinetic and potential energy. Most of the time they have the lowest point in the track as the reference level, but it's important to establish a reference level when we're talking about gravitational potential energy. So really quick here before we get to a couple of examples, we will talk about elastic potential energy and other forms of energy. So I talked about this already, but it's pretty important. It's really something that we use quite a bit. It's used in toys, it's used in hunting, it's used in simple things like rubber bands, like organizational tools. But elastic potential energy is stored energy in something that is rubberized or something like that, or some kind of a spring. Okay, it's often rubber balls, rubber bands, slingshot, and trampolines. Springs, like I said, there's springs in almost every single motor, every single car. We use elastic potential energy a lot. So at this point in time, 2020, things are characterized like springs are given values when you buy them. There's spring constants and stuff like that, so you know exactly what spring to buy. But when we created certain springs, or when we are creating more springs, we have to figure out the elastic potential energy of those springs in order to use them in this certain scenario. So this next slide here just talks about other forms of energy, which you can look more up on these. I'm not going to go into depth, but chemical energy is released from burning of fossil fuels. So that would be when you drive your car and you burn gasoline. Nuclear energy is released when the structure of an atom's nucleus changes. Nuclear energy is released when the structure of an atom's nucleus changes. So this could be in maybe radioactive decay, something like that, that releases nuclear energy. When we crush particles together and they explode. A nuclear power plant, you can look up more how that operates, but we use We use hydrogen atoms and stuff like that in order to create nuclear energy. And thermal energy can be written as the sum of the kinetic energy and potential energy of the particles in a system. And we have this one highlighted because if you take your hands and rub them together, this is kind of an example of thermal energy. If you do it really slow, you're not really going to create much heat. But then you take your hands and you rub them really quick, then you will create more thermal energy. So more kinetic energy will result in more thermal energy. All right? And more potential energy will also result in more thermal energy because that potential energy is more than likely going to be transferred into or will be changed into kinetic energy. Okay, so thermal energy is something we use quite a bit. We have our furnaces, we have electrical systems. Those create thermal energy. Sometimes we want to avoid thermal energy, sometimes we want to use thermal energy. So it really depends on the scenario. We have a few more down below. We have radiant energy, so that is carried by electromagnetic waves. Electrical energy associated with charged particles, so that would be with the movement of charged particles. And mass, so this one kind of gets into Einstein's theories of mass can be turned into energy when it's moving at the speed of light. So that's the E equals mc squared, which you could write books on this stuff. So if you want to look this up, go ahead. You can read about it. There's wiki pages all over the place, and there's scholarly articles and that good stuff all over the place for mass being turned into energy. Okay. Let's take a look at a few problems here. We are using gravitational potential energy, and we're going to be using kinetic energy. So let's see if we can make some sense of these. The scenario: you lift a 7.3 kilogram bowling ball from the storage rack and hold it up to your shoulder. The storage rack is 0.610 meters above the floor, and your shoulder is 1.12 meters above the floor. So we have our scenario here. Rack, the average height, I suppose, is 0.610, and then our shoulder is 1.12. So we have A, B, and C. Let's write these out, see if we can figure them out. So when the bowling ball is at your shoulder, what is the ball-earth system's gravitational potential energy relative to the floor? So this piece here might be slightly confusing, but that would be comparing the ball to the ground or the earth, okay? We're not talking about the concrete floor or anything. We're just saying ball to the earth, and we're going to use the values that we're given. So when the ball is at your shoulder, what is the ball-earth gravitational potential energy? So let's write some things we know. We have a mass of 7.3 kilograms, and then at your shoulder, the height is going to be 1.12 meters. And then we need to write out our equation if we don't remember. So GPE, gravitational potential energy, equals mass times gravity times height. So we actually have all three variables. I'll write out G here for you, so we remember it. So it's 9.8 meters per second squared, and it's just pretty much as easy as plugging in everything that I have there. So I put in my mass, my height, and my gravitational constant, and then we're going to put those in our calculator to get what our gravitational potential energy is going to be. So for this one, we're going to get 80.1248, so we'll say 12 joules. So when we have the ball up at our shoulder, we have 80.12 joules of gravitational potential energy on the ball. So for the second one, when the ball is at your shoulder, what is the ball-earth systems of gravitational potential energy relative to the rack? So now we're trying to figure out what's the potential energy relative to the rack right there. So this is our reference point of 0, if you remember that. So that's our height of 0. So what we're going to have to do is figure out this height right here. So 1.12 minus 0.610. So we have our equation right there. We're just going to write out everything as we have it, and then we can just kind of throw it in our calculator. So it's mass, which is 7.3 kilograms, times gravity, which is 9.8 meters per second squared, times our height. So it's 1.12 meters minus 0.610 meters. So if we put all this in our calculator, we'll get the gravitational potential energy for that system with that reference point there. is going to be 36.4854, so we'll say 49 joules. So that's our GPE when we compare it to the reference level of the rack. Alright, so with question C, how much work was done by gravity as you lifted the ball from the rack to your shoulder level? So, going on our lesson yesterday, we have work equals force times the distance. And we're going to have to plug some stuff in there. So we know that the force from gravity is going to be 7.3 kilograms. And this is kind of tricky here with our signs because I'm lifting the ball up. So gravity is pulling down. So my force is going to be a negative 9.8 meters per second. So I have to involve signs when I'm doing work with this one. And then the distance that I move it, again, just like last time, like our letter B here, 1.12. And the distance, just like in B, we're going to have to take the difference between 1.12 and 0.61 because this is the distance that I'm actually moving the ball. I'm lifting it from the rack to my shoulder height. So I'm going to write that down in here again. 1.12 meters minus 0.61 meters. And when you put that in your calculator, you get a negative 36.49 joules. So that is the value for work. All right, so if you compare these two, just like our last lesson, kinetic energy is so if you compare these two, just like our last lesson, kinetic energy is connected to how work is done. Potential energy can also be connected to how work is done. So these are the same values, but it depends on our reference level and it depends on what we're looking at. Work done by a person or work done by gravity. So let's look at another example here. So how much work does a bricklayer do to carry 30.2 kilograms of bricks from the ground up to the third floor, a height of 11.1 meters, of a building under construction? What's the gravitational potential energy of the brick earth system when the bricklayer reaches the third floor? So the third floor is that 11.1 meters, and the mass that is moving is 30.2 kilograms. So we're going to use, we have our gravitational constant again, G equals 9.8 meters per second squared. So we want to find gravitational potential energy. So our equation is pretty simple. It's mgh, mass times gravity times height. We're moving 30.2 kilograms of bricks. And we have gravity acting on that. And we're moving it a height of 11.1 meters. So we're just going to use those values to find our gravitational potential energy. So when we get those bricks to the top, we have a gravitational potential energy of 3,285.16 joules. So that is the gravitational potential energy of those bricks when we get them to the top. So the last example we're going to look at here involves rotational kinetic energy. And if you forgot what our equations were for rotational kinetic energy, we have them off to the side here. So we'll bring this out. So we're going to need inertia, and we're going to need our value for kinetic energy in a rotational system. So let's read our problem here. So a 7 kilogram disc with a radius of 0.8 meters is spinning at an angular speed of 1.5 RPMs, or revolutions per minute. What is the rotational inertia of the disc? And what is the rotational kinetic energy of the disc? So we have a little bit of work to do here. Let's start with A, rotational inertia of the disc. So that's 1/2 mr squared. We can figure that out pretty quick, right? So 1/2 times my mass, 7 kilograms, times my radius, 0.8 meters, squared. And that's going to give us 2.24. And that's kilograms times meters squared. So you remember your units for moment of inertia or rotational inertia here. All right, so that's going to help us figure out B. What's the rotational kinetic energy of the disk? So we have our equation right there. All right, kinetic energy, and we'll just write a R for rotational, is 1/2 times inertia, 2.24 kilograms times meters squared. times our omega, which is going to be our rotational velocity or angular velocity. So we have 1.5 RPMs, and that is 1.5 revolutions per minute, right? So we need to change that to radians per second. All right, so that's what everything needs to be in when it wants to work together. So we need to change revolutions per minute to radians per second. So in order to do that, remember, we have one revolution is 2 pi radians. That's going to be our first conversion, get rid of those revolutions. And then we're going to go from minutes to seconds. So 1 minute is 60 seconds. So that'll get rid of our minutes, and we're ending up with radians per second. Okay, so when you put that in your calculator, you're going to get 0.16 radians per second, which is the appropriate value that we want for omega, or our angular velocity. So let's put that in here. And I have the exact value stored in my calculator. So this is what I'm going to use to get my kinetic energy in a rotational system, or rotational kinetic energy. And that will give us 0.028 joules of rotational kinetic energy in the system. All right, so it's kind of a smaller number, but if you're thinking about it, the thing is staying in place and it's rotating. So generally our rotational kinetic energy will be smaller, and this is actually pretty slow. All right, if we had like a motor or a flywheel on a motor, that thing is going to be going thousands of revolutions per second. So, or revolutions per minute. So that would be quite a bit higher, but this is going fairly slow. Okay, so we've discussed potential energy and kinetic energy in different systems, and along with different types of energy. So hopefully this helps you in learning about different forms of energy. Thanks for watching.